Swayam Prabha. Digital India. Educated India.
Well, in this particular lecture, we are going to discuss the simplex method, shadow prices, and the B inverse matrix. Now, as the name suggests, the shadow prices and the B inverse matrix are very important concepts. They are, which can interpret the linear programming problem, which has been already solved by the simplex method. The shadow prices are basically the Cj minus Zj values, the absolute values of the Cj minus Zj values of the final table. And these shadow prices are very important in obtaining the effect of additional resources if they are available. So which will come very handy in the sensitivity analysis. Later on, we shall see that these shadow prices are nothing but the solutions to the dual problem. Obviously, at this point, we do not know what is a dual problem, but dual problems are associated with the original problem. Every linear programming problem can be solved by two different ways, right? A maximization problem can also be solved as a minimization problem by suitable transformation. So that is usually is the dual problem, and the shadow prices are basically the solutions to the dual problem. The B inverse matrix on the other side is a matrix which is formed by the original slack variables, or the variables they are in the basis in the first table of the simplex method that we are following. And B inverse matrix is also very important to do sensitivity analysis in the sense that if we have the B inverse matrix, if we already know it, and if we multiply by the columns of the original problem, then original simplex table, then that will help us in obtaining the final table. Is it all right? So that is how the B inverse matrix is also very important. If we know the B inverse matrix, that is the inverse of the basis matrix formed by the variables in the basis of the final table in the original table. Anyhow, so we shall see all these, and as before, we shall take an example based method. So we start with an example, and with the help of that example, we shall try to explain these concepts. So here is that example, and this example you have already seen before. It is the same example that we have already solved. So without spending much time, let me very quickly say that it's a product mix problem. There are two products, A and B, and there are three resources: forming, welding, and painting. If only A would have been produced, we could have made 90, 80, or 150 respectively from these three resources, and if only B would have been produced, then we could have made 120, 160, or 100 number of items for the product B. And the profit coefficients are rupees 600 and rupees 400 per unit respectively. We need to find out the optimal production per day of these two products so as to maximize profit. So the intercept method, as you already we discussed, that supposing x1 and x2 are the number of product A and product B that have been produced. So with regard to the forming resource, it could be 90A or 120B. So x1, if we are producing, so x1 by 90 is the share of A, and x2 by 120 is the share of B. So x1 by 90 plus x2 by 120 should be less than equal to 1. And same thing about the other ratios, that is x1 by 80 plus x2 by 160 should be less than equal to 1, and x1 by 150 plus x2 by 100 should be less than equal to 1. What we have done, we have simplified this, and these are written in this manner. That is 4x1 plus 3x2 less than equal to 360, 2x1 plus x2 less than equal to 160, 2x1 plus 3x2 less than equal to 300. So these are our constraints, and non-negativity constraints are x1 greater than equal to 0 and x2 greater than equal to 0. And objective function maximize z equal to 600 x1 plus 400 x2. That is our original problem. The original problem is, one of maximization. All the constraints are less than equal to, and there is also a non-negativity constraint. So if we want to solve it by the simplex method, we know that we have to add the slack variables. Now, 3 slack variables are added. In the first constraint, let us say the slack variable is x3. The second constant x4, and third constant is x5. So what has happened? The inequalities have turned to equalities, and we have now 3 equality constraints and 5 unknowns, and all these 5 variables are non-negative, and the objective function also, they participate with different profit coefficients. X1 and X2 have real coefficients like 600 and 400, and slack variables, they do not have any profit coefficient, they are all zeros. One interesting thing, as you know, for any simplex problem, the simplex problem, initially we know that we cannot solve the problem without putting some of the variables to zeros. So those variables which are put to zeros initially, to x1 and x2, both are put to zeros. Then the solution for x3, x4 and x5 can be found. So x3 and x4 and x5 are called to be in the basis, and x1 and x2 are called to be in the non-basic variables. So we also know that the variables in the basis, they form an unity matrix, that is 1 0 0 0 1 0 and 0 0 1, and that is said to be that these constraints are in canonical form. So this canonical form is a very important part of the simplex method, and we drop one of the basic variables to the non-basic, and one of the non-basic variable we bring to the basis, and again those variables in the basis and non-basis, that has to be put in a canonical form. That means the variables in the basis should again form an unity matrix, and that is done by the pivot operation, and this pivot operation is central to the simplex method. All these things we have already discussed, and we have also seen some examples, and further examples we shall also discuss in our next class. But in this particular class, let us see the solutions, create the solutions from the shadow price and the B inverse matrix point of view. All right, so this is our simplex first table. So this we already know that x3, x4, x5, they're in the basis. 360, 160 and 300, those are the values. The x3, x4, x5, the variables that are in the basis, they form an unity matrix 1 0 0 0 1 0 and 0 0 1. The variables not in the basis, that is the non-basic variables, are x1 and x2. X1 coefficients are 4 2 2, x2 coefficients are 3 1 3. That means to make 1 unit of x1, I need 4 units of x3 resource, 2 units of x4 resource, and 2 units of x5 resource. Similarly for x2 also, that is 3 1 and 3. The profit coefficients are 600 and 400, and these are all zeros, and therefore the loss profit per unit Zj should be 0 and 0, because the currently x3, x4, x5, they're in the basis and they are associated with 0 profit coefficients. So net profit per unit for x1, it is 600 minus 0, that is 600, and for x2 it is 400 minus 0, that is 400. All right. So therefore, what we find is that the simplex first table is obtained. Thereafter, we find the entering variable. In this case, it should be x1, and leaving variable, it should be x4. because that is the bottleneck resource. Anyhow, like this, the simplex method goes on, and after solving the simplex, because we have already done this problem earlier, this is the final table that we have found in the optimum table. So what is the final solution? X2 equal to 40, X1 equal to 60, and X5 equal to 60. Since X2, X1 and X5 are in the basis, in that order, they form the unity matrix x2 100, x1 010, and x5 001. x3 and x4 are said to be in the non-basis because they are the non-basic variables. Their coefficient values are there. And if we then compute the zj and cj minus zj for these variables, you can find out 400 into 1 plus 600 into minus half, that is equal to 100. And 400 into minus 2 plus 600 into 3 by 2 plus 0 into 3, 100. All right, so both the zj's are 100. Since cj values are zeros, so cj minus zj values would be minus 100 and minus 100 respectively. So as all the cj minus zj values are negative for a maximization problem, we have found the optimum solution, that is x1 star equal to 60 and x2 star equal to 40 and z star equal to 52,000. Basic variables at this point are x2, x1 and x5. Non-basic variables are x3 and x4. Observe the unity matrix formed by the variables in the basis in the coefficient matrix. Already we have seen that. Could you find that the table is in canonical form? Yes, it is in canonical form. Note the order of the basic variables also, because in that order only we have to find the canonical form, or we have to find the unity matrix. Right. So having said that, the simplex final table is obtained. Now a very interesting thing, that is the shadow price. Now these absolute values, you see these x3, x4 and x5, they represent our three resources. Originally there are three resources, R1, R2 and R3, and the shadow prices are with respect to these three resources. So what are those values? They are minus 100, minus 100 and 0. So absolute values of cj minus zj pertaining to the slack variables in the final simplex table. Now here the absolute values are important because after all there should be all positive, right? So cj minus zj values, they should be all positive. So if there are some negative values, we have to discard the negative sign and we have to take the absolute value. So absolute value of the cj minus zj pertaining to the slack variables in the final simplex table, they are called the shadow prices. Now what is the significance of the shadow prices, right? With regard to the corresponding resources. So what are they, right? So that is the question that we ask, and that we have to look at. So you see here, these are the shadow prices that has been shown. This is the final table. This is the original problem, and x3, x4, x5 are the slack variables associated in the original problem, and slack x3, x4 and x5. cj minus zj of the final table, minus 100, minus 100 and 0. Three resources R1, R2, R3 are associated, and the shadow prices then should be 100, 100 and 0 respectively. All right, so what are shadow prices? I think you are very clear. Once again, let me repeat. The original slack variables from the original table, they will be only having the shadow prices, and these shadow prices are basically absolute values of the cj minus zj in the final table. Is it not? Who are having these shadow prices? The corresponding resources. Right. Now, having said that, something very interesting you will be able to find. So what you find, that optimum solution is x1 star equal to 60 x2 star equal to 40 and z star equal to 52,000. Now, these optimal solutions, suppose you put in the original constraints, what do you find? The interesting thing, let us put them in the original constraints. So, supposing you put x1 equal to 60 and x2 equal to 40 in the first constraint, what do you find? 4 into 60, how much? 240. 3 into 40, how much? 120. So what is the total? 240 plus 120, 360. So what has happened? When you put this optimum solution 60 and 40 in the first constraint, you find that LHS and RHS, they become equal. So that means if the optimum solution that has been obtained, that is put with regard to the first constraint to which the resource R1 is there, that constraint turns to equality. Now let us see the second constraint, x1 60, x2 equal to 40, and so 60 into 2, 120 plus 40, 160. Look again, the LHS and RHS have become equal. That means if the optimum solution is put in the second constraint also turns to equality. Let us put them in the third constraint and see what happens. 60 into 2, 120, 40 into 3, 120, 240. So it is not equal. In fact, the gap is 60. And if you go back to our final solution, can you see that x3 equal to 0 because that is non-basic, x4 equal to 0 because it is non-basic, and x5 equal to 60. Right? Just look here, the final solution x5 equal to 60. And here what you got? 2x1 plus 3x2 equal to 240. So exactly that 60 gap in x5. So x5 equal to 60 at the final table. So I think you can interpret, but basically, one thing we found out that if we put the optimum solution in the original problem, we found that with regard to resource R1, that is the first constraint, that has turned to equality. With regard to resource R2, second constraint has also turned to equality, but the third constraint has not turned to equality. This is what we have found out. That is our interesting observation. So, this is exactly what we are written here, that optimum solution is x1 equal to 60, x2 equal to 40, z star is 52,000. Putting optimum solution in the three constraints of the original problem, we find constraints related to R1 and R2 turns to equality. Look here. Now, shadow prices are R1 has a shadow price that is 100, R2 has a shadow price that is 100, R3 doesn't have a shadow price, it is 0 only. Is it not? So if there is a shadow price which is non-zero, positive quantity, then the corresponding primal constraint turns to equality. So in another word, if slack vanishes, so here slack has vanished. So if slack vanishes, the constant turns to equality, the shadow price exists. Or in the reverse, if the shadow price exists, then the slack should vanish. Is it all right? So, this is a very important observation with regard to the shadow price. So when there is a shadow price of a particular resource, that means that resource has been exhausted. That means that particular constraint has turned to equality. That means there is no excess resource that is available. But there is no shadow price for R3. That means R3 is not exhausted. In fact, R3 is 60. That means after producing 60 quantity of X1 and 40 quantity of X2, while the resource R1 and R2 have exhausted, R3 is not exhausted and a value of 60 is remaining with regard to the R3. Is it not? So this is what exactly is the interesting observation that we have found with regard to the shadow prices. Now another very important observation, the shadow prices are also dual solutions. Now why they are called dual solutions? Let us see. that we have found out the optimum solution as x1 equal to 60, x2 equal to 40, and z equal to 52,000. Now, how much of the original resources we had? The resource R1 was 360, R2 was 160, R3 was 300. Now, what are their shadow prices? 100, 100, and 0. Let us multiply them. So 360 into 100, 160 into 100, and 300 into 0. How much is that? That value is also 52,000. Right? So you see, if we look at the shadow prices, from there also we can find out the at least the Z value of the optimum solution. In fact, the shadow prices are dual solutions. So as I said, like this original problem, which is a maximization problem, it is actually associated with a dual problem, which is will be one of minimization. And for that particular problem, if we solve with regard to simplex or any other method, then that solution will be 100, 100, and 0. Is it all right? So that means, these dual solutions, from there also we can find out the value of Z, and the same Z value would be returned from the shadow prices also. So this is a very important and interesting observation, and let us see how it could be useful. Now you see the shadow prices are also called the marginal prices. So how they are marginal prices? They are marginal prices because suppose an extra amount is available, right? So you see the original solution is 60, 40, and 52,000, and from the shadow prices also we can find out those values. That is 360 into 100 plus 160 into 100 plus 300 into 0, that is 52,000. But suppose we have the resource 1 available at 370, right, instead of 360. What would be the new optimum solution, right? So you see, because now we know the shadow price for the resource 1 is 100, and if 10 more resources are available, that means 360 to 370, additional profit that we are going to gain is 10 into 100. Right? So that 10 into 100, another 1000 additional profit we can add, and you get 52,000 plus 1000, that is 53,000. That should be the new value of Z star. So interestingly, since the shadow price still will exist for R1 and R2 and no shadow price for R3, that means the first two constant will become then equality. That means 4x1 plus 3x2 equal to 3, and 2x1 plus x2 equal to 160. So if we solve them, it's very simple. We have to just multiply these by 2. So that will be 320, and that is 370. So deduct then 4x1 minus 4x1 and 3x2 minus 2x2, that means x2. So x2 will become 50. And because x2 is 50, so then 2x1 plus 50 equal to 160. So 2x1 equal to 160 minus 50, that is 110. So x1 will be 55. So that new solution will be then x1 star equal to 55, x2 star equal to 50, and z star will be 53,000. Right? So you can just look here. We need not solve the problem. If the 360 becomes 370, straight away we can obtain the new solution, and from the shadow price we can also find out the value of the Z star. So what would be the new value of Z star from shadow prices? It should be 370 into 100 plus 160 into 100. So 37,000 plus 16,000 equal to 53,000 again. Is it all right? So you can see that why the shadow prices are important, and what is exactly it means that the shadow prices are basically the nothing but the marginal prices, and how sensitivity can be obtained from the shadow prices. But obviously one should also remember that you cannot do it ad infinitum, because at some point what will happen, some other constant will become bottleneck, right? Currently, you see the resource R3 was in excess of 60 quantity. But now when we have the solution 55 and 50, what has happened? 55 into 210 and 50 into 3, 150. So this value become 260. That means the resource R3 has now become 300 minus 260 equal to 40. So already the resource, third resource, that is resource R3, has reduced from 60 to 40. All right. So at some point it will become bottleneck resource, and therefore we cannot keep on doing this sensitivity analysis. There would be a limit. Till such point you can do it. So there are limits to which such sensitivity analysis can be carried out. So anyhow, for small values, we can always work out and we can check these three constraints and see that what would be the impact of a small change in the resource values, and we can work them out. Right. Now let us look at the B inverse matrix. You see the final table. Once again, the final table has been reproduced. In the final table, one thing you can see that the basic variables of the first table. So what are the basic variables of the first table? If you recall, the basic variables in the first table were the slack variables, that is x3, x4 and x5. So the matrix that is formed by basic variables of the first table in the final table. So the language looks a little cryptic, but you have to be careful. The basic variables of the first table. So in the first table, the basic variables were x3, x4 and x5. So the matrix that is formed by those variables in those columns, if you take, though, that is called the B inverse matrix. So what is the value of the B inverse matrix for this problem? It is 1 minus 2 0, that is 1 minus 2 0, minus half 3 by 2 0, minus 2 3 and 1. So that is what is written here. So that is the B inverse matrix. Is it not? So naturally the question comes that if this is B inverse matrix, then what is B matrix then? Is it not? Because if there is an inverse of a matrix, that means there is an original matrix somewhere. So what is that original matrix? All right, we have the inverse matrix. So what is the original matrix B? In fact, the original matrix B is the matrix. It is, see carefully you hear, the B matrix is the matrix formed by the basic variables of the final table in the first table. So what are the basic variables of the final table? X2, x1 and x5. So the values that we had of x2, x1 and x5 under those columns in the original, that is the first table. So that matrix is the B matrix. Is it not? So B inverse matrix, it is the matrix formed by the basic variables of the first table in the final table, and B matrix, it is the matrix formed by the basic variables of the final table in the first table. So this is the fine difference. So this is written here, and here it is the first table, here it is the second table, sorry, the optimum table, the final table, first table and the final table. So B matrix, it is the matrix formed by the basic variables of the final table in the first table in that order. That order is important because look here, what are the variables in the basis in the final table? X2, x1 and x5. So x2, x1 and x5. Now what is the column under x2 in the first table? 3, 1, 3. So we wrote 3, 1, 3. What is the variable under x1 in the first table? 4, 2, 2. So we wrote 4, 2, 2. What is the column under x5 in the first table? 0, 0, 1. So look, 0, 0, 1. So that is written here. So once again, the B matrix is the matrix formed by the variables in the basis of the final table in the first table, and B inverse matrix, that is this one, that is the matrix formed by the variables in the basis of the first table in the final table. Now what happened? What is this happening? How exactly? Now what is the, what is B inverse? What is the meaning of B inverse? You also have read how to invert a matrix, is it not? So if we invert a matrix B, that means this matrix B, if we invert, we are going to get this matrix, that is B inverse matrix. So very interestingly, that means the simplex process is such which actually inverts the basis matrix, is it not? So basis matrix is B. B is formed by the variables in the basis in the first table, and that same matrix B is inverted to another matrix which is the B inverse matrix in the final table. So exactly how it has happened? What is the mechanism, or what is the process by which this has happened? Let us try to understand the process. You see, there is a procedure which actually says that suppose if I can write a matrix in the form B concatenation I, where I is the unity matrix of the same order, then suppose by some matrix operation we can make this part by suitable matrix operation by adding, subtracting, and those kind of things. If we convert B to I, then I will become B inverse. So these you already know. Now look here, what has exactly happened? The variables in the basis of the final table are x2, x1, and x5. So x2, x1, and x5 in that order. Now suppose I think of the original matrix as a concatenation of these B matrix and these unity matrix, which is formed by the x3, x4, and x5. So B is formed by x2, x1, and x5 in that order, and I is the unity matrix formed by x3, x4, x5. Now that B which is there, that is x2, x1, and x5 in that order, that means the B matrix which we had earlier, that means this matrix 3 1 3 4 2 2 0 0 1. What has happened to that matrix in the final table in that order x2, x1, x5? You see, it has become 1 0 0 0 1 0 and 0 0 1. That means it has become an unity matrix. That means the original matrix B has become an unity matrix I. So now look at the rule. The rule says that if the matrix B concatenate I, then you convert B to I, then I will convert to B inverse. So what has I become? The I is the original unity matrix in the first table, that is 1 0 0 0 1 0 and 0 0 1. What it has become? It has become 1 minus 2 0 minus half 3 by 2 0 minus 2 3 and 1. All right, so in a sense that B inverse matrix has actually converted to the B inverse. B matrix has converted, that is to the B inverse matrix of the final table. So that is exactly the first table is B concatenate I. B is formed by x2, x1, and x5 in that order, and I is the unity matrix formed by x3, x4, and x5. And in the final table is I concatenate B inverse. I is the unity matrix formed by x2, x1, and x5 in that order, and B inverse is formed by x3, x4, and x5. I hope you understood that what is B and what is B inverse. To understand that, once again, let me repeat it. The B inverse matrix is the matrix formed by the basic variables of the first table in the final table, and B matrix is the matrix formed the basic variables of the final table in the first table in that order. All right, so hopefully you have now understood the B matrix and B inverse matrix, and you have also understood that how the simplex procedure from the first table to final table is a process of matrix inversion. And this matrix inversion, because the B has become I, so therefore I will become B inverse. All right. So what is the significance of this B inverse? So you see it has a very interesting and important significance. That what is that particular significance? The significance is that if we multiply the B inverse matrix with any column of the first table, then corresponding final table column we shall get. So let us first talk about the values. So this is the value. So value is 360, 160 and 300. Let us multiply, pre-multiply these values with B inverse. So B inverse B equal to B dash. B dash is these values. So look here, this is the B matrix 1, minus 2 and 0, minus half 3 by 2 and 0, minus 2, 3 and 1. So when you multiply that with 360, 160 and 300, what exactly you get? What exactly you get is that you get the values, that is 1 into 360 into minus 2 into 160 and 0 into 300. Right, so that is precisely what you get. So that means 1 into 360 and minus 2 into 160, so 360 minus 320, it is equal to 40. Then minus half into 360, that is minus 180, and 3 by 2 into 160, that is 240, and then it will 240 minus 180, it will become 60. And the last one, minus 2 into 360 minus 720 plus 160 into 3, 480 plus 300. So that will become 60. Right. So what has happened? We have multiplied B inverse matrix with these values and we got the final table values. That means, you see, look here, suppose you are told that x2, x1 and x5 are going to be in the basis of the final table in that order, and then you can form the B matrix from the first table. All you know is what are the variables that are going to be in the basis of the final table. Suppose you know this. Then, with that knowledge, you can obtain the B matrix, you can invert the B matrix, then you get the B inverse matrix, and then you can multiply every column of the first table, you can create the final table. Is it all right? So this is the significance of the B inverse matrix. So applying B inverse matrix with any column of the first table gives us the final table. That is also true. So A1 is the x1 column of the first table and A1 dash is the x1 column of the final table. So B inverse A1 equal to A1 dash. All right, so B inverse A1 equal to A1 dash. So that means 1 minus 2 0 minus half 3 by 2 0 minus 2 3 1 into 4 2 2. See, that is the x1 column. It should return 0 1 0. We can cross check 1 into 4 minus 2 into 2, that is 4 minus 4, and 0 into 2 is 0. So we get 0. Then minus half into 4, 3 by 2 into 2. So 3 by 2 into 2 is 3 and minus half into 4 is minus 3. So sorry, minus 2. So 3 minus 2, 1. This one is 0. And then minus 2 into 4, minus 8. 3 into 2, 6. 1 into 2, 8. 2. So 2 plus 6, 8 and 8 cancels. So 0. So you see that pre-multiplying the B inverse with this column returns this column. So it will happen for every column of the final table, and this is the specific advantage of the B inverse matrix. And how you can use it for sensitivity analysis? Again, let us say that the value pertaining to the x3 changes to 370. Right, instead of 360 it becomes 370. What would be the new optimum solution? So you see that is also possible to compute by pre-multiplying with the B inverse. So not only with the existing value but also with the changed values, the B inverse matrix can be useful. So see, multiply B inverse matrix with these values, then you will get 1 into 370 minus 160 into 2, that is minus 320, 0 into 300, so 50, is it not? And minus half into 370, 3 by 2 into 160, 0 into 300, you will get 55. All right, so you get 50, 55 and 40, minus 2 into 370, 3 into 160 and 1 into 300. So this 50, 55 and 40, that is the new solution. X2 equal to 50, x1 star equal to 55 and x5 star equal to 40. That means Z star will be 53,000. So that is the importance of the B inverse matrix. The B inverse matrix can be useful, and there is a method called the revised simplex method, which actually finds the leaving variable and the entering variable, and from there the B matrix is obtained, and from B matrix the B inverse matrix is obtained by inverting the matrix, and from there, from any table, the next table can be obtained. Is it all right? So those are the advantages, and also the B inverse matrix can be used for sensitivity analysis. Right, so in this particular lecture we have already learned two very important techniques, the shadow price and the B inverse matrix, and these matrices and the shadow price, they are useful in interpreting and linear programming problem. All right, so now that we learned these two techniques, let us see one more problem and also try to see how those B inverse matrix and the shadow prices are useful with regard to the second LP problem also. So what happens in this particular LP problem? ABC produces two models of an assembled product that use milling, drilling and grinding facilities respectively. The table below shows the details for the next plan period. What are the resources? Milling in machine hours, drilling in machine hours, grinding in machine hours. How much is required for model 1, 2 and 3, model 2, 2 and 1, and model for grinding 0 and 4. And sorry, for milling 2 and 3, for drilling 2 and 1, and for grinding 0 and 4. And the profit coefficients are 30 and 40 per unit respectively. And how much is maximum available? 1200, 1000 and 800. So find optimum number of models to be produced by using the simplex method. So what is the objective function? What are the decision variables? First of all, can you see that decision variables are x1 and x2? x1 is the number of model 1 to be produced. x2 is the number of model 2 to be produced. What is the objective function? It should be 30x1 plus 40x2. Then what is the milling machine constant? That should be how much? 2x1 plus 3x2 less than equal to 1200. Drilling machine constant 2x1 plus x2 less than equal to 1000. And finally the grinding machine constant, that should be 4x2 should be less than equal to 800. Right. So that has been written here. The decision variables: x1 number of model 1 produced, x2 number of model 2 produced, sorry, not model 1, model 2 produced. Objective function: maximize z equal to 30x1 plus 40x2. Constraints: milling hour constraints 2x1 plus 3x2 less than equal to 1200. Drilling hours constraints 2x1 plus x2 less than equal to 1000. Grinding hour constraints 4x2 less than equal to 800. And the non-negativity constraints x1 greater than equal to 0 and x2 greater than equal to 0. So first of all, we have to find the augmented problem, right? So what is the augmented problem? The augmented problem would be maximize z equal to, so 3 slack variables we add, x3, x4 and x5, right? So and then we get these equations: 2x1 plus 3x2 plus x3 equal to 1200, 2x1 plus x2 plus x4 equal to 1000, 4x2 plus x5 equal to 800, and this is our objective function, and these are the non-negativity constraints. Now from there we can write the simplex first table. So once again, the simplex first table, the basic variables are x3, x4, x5. The values are 1200, 1800. Basic variables are x3, x4, x5. They form unity matrix so that the entire matrix is in canonical form. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. The profit coefficients are 30 and 40. And here for the basis variables, they are all zeros. So Zj should be lost profit per unit should be all zeros. 2 into 0, 2 into 0, and 0 into 0, 0. 3 into 0, 1 into 0, and 4 into 0 equal to 0. So Cj minus Zj should be 30 and 40. So this would be a good simplex exercise also. So which one should be our entering variable and which one should be our leaving variable? Just think and tell me which one should be the entering variable. Can you see that x2 should be the entering variable because the Cj minus Zj value is higher. So x2 will be our entering variable. Now which resource becomes bottleneck? You know, x3, x4 or x5? Please look at it carefully. 1200 by 3, 1000 by 1, and 800 by 4. So which one is the minimum? No, just see 1200 by 3, that is 400. 1000 by 1 is 1000, and 800 by 4, that is 200. So that means x5 should be our leaving variable. So precisely that is what is shown here, that x5 is our leaving variable, x2 should be our entering variable. Then what we do, we divide this key row by the intersecting element, which is the 4, and all items are obtained accordingly. 800 by 4 is 200, 0, 4 by 4 is 1, 0 by 4 is 0, 0 by 4 is 0, and 1 by 4 is 1 by 4. All right, then the key column we see, in the key column it should be then 0, 0, 1. Intersecting element is now 1, so other items should be 0. So then we look at the basic variables x3, x4, x2 in that order. So x3 100, x4 010, and x2 001. So the unity matrix is also obtained with regard to the basic variables. Then we have to compute the non-basic variable coefficients. So these two should be 2 minus 0 into 3 by 4, so 2. These two should be 2 minus 0 into 1 by 4, so 2. Right? This 0 should be 0 minus 3 into 1 by 4, minus 3 by 4. This 0 should be 0 minus 1 into 1 by 4, so minus 1 by 4. Alright, so all these are calculated. In fact, these Cj minus Zj values can also be computed by the formula. So this 30 minus 40 into 0 by 4, so 30. And this 0 should be 0 minus 40 into 1 by 4, so minus 10. Alright, so the formula once again, new element equal to old element minus corresponding key row element into corresponding key column element divided by the intersecting element. So all these rules have been applied, and using these rules we have got the simplex second table from the simplex first table. Now from the simplex, once again, that you can tell which one should be our entering variable and which one should be our leaving variable. Can you see that the entering variable is x1? Now why x1 should be the entering variable? Because Cj minus Zj value is maximum. Not only maximum, it is positive. So there will be increase in profit. This is minus 10, so discarded. So x1 should be the entering variable. So which one is the bottleneck resource at this point? Is it x2 or x4 or x3? Because 600 by 2 is 300, 800 by 2 is 400, and 200 by 0. So obviously resource is not required. So can you see that x3 is going to be our leaving variable? All right. So if you understood that x3 is going to be our leaving variable because that ratio is the minimum, and x1 is going to be our entering variable. Now the intersecting element is 2, so we divide all items by 2, and then we get x1 300, 600 by 2, 2 by 1, that should be 1, 0 by 2, 0, 1 by 2, half, 0 by 2, 0, and minus 3 by 4 by 2, minus 3 by 8. Alright, so that is where the third table we are getting. And then the basic variables, they should form unity matrix, x1, 1, 0, 0, x 0, and x2, 0, 0, 1. All right, so we get the unity matrix also, and thereafter we have to compute variable values for the non-basic variables. So non-basic variables here are x3 and x5. So x3 already key row we have taken care of. So these 0 should be 0 minus 2 into 1 by 2. So that means minus 1. And these 0 should be 0 minus 0 into 1 by 2. So no change, 0. And here this minus 1 by 4 minus 2 into minus 3 by 4 into 2. So that means minus 1 by 4 plus 3 by 4. So it should be half. And no change here because after all there is a 0. So if there is a 0 in the key row or the key column corresponding element, then no change happens. So there is no change. And once again we can compute Cj minus Zj's also. See, originally for x3 it was 0, so 0 minus 30 into 1 by 2, so minus 15. And here minus 10 into 30 into minus 3, 4 minus of divided by 2, right? So that means 30 by 2, 15, 15 into 3 by 4. So that is 45 by 4. So 45 by 4 minus 10, so 45 by 40 by 4, that means 5 by 4. All right, so interestingly, we get a positive Cj minus Zj for x5. So is there any variable that is going to enter now? Which variable should be entering? Can you see that it is x5? Because we have a positive Cj minus Zj in a maximization problem. This one is minus, so not considered. So x5 should be the entering variable. And which one is our bottleneck resource? Obviously not x1 because it is a negative. So the negative value, so resource is given, resource is not required. So cannot be bottleneck resource. 200 by half, so it becomes 400, and 200 by 1 by 4, it will become 800. So that means x4 is going to be our bottleneck resource. So x5 comes in, x4 goes out. So that would give us our next table, and as correctly we have seen that x4 gets into the basis, and from x5 gets into the basis, and x4 goes out of the basis. So thereafter let us see then the values first of all. So the key row element has to be divided by the intersecting element half. So 200 becomes 400, 0, 0 remains 0, 0, minus 1 becomes minus 2, 1 becomes 2, and half becomes 1. And then the basic variables will form unity matrix in that order: x1, x5, x2, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And remaining elements we compute by the method. What is that method? Half minus 1 into minus 3 by 8 by half. So it becomes minus 1 by 4. 0, 0 minus 1 into minus 3 by 8 by half. So it becomes 3 by 4. Anyhow, like this, these variables are computed, and this time we find all the Cj minus Zj values are negative. Right? So all the Cj minus Zj values are negative. So what happens then? The Cj minus Zj values, since all are negative, the optimum solution is obtained. And what are the optimum solutions at this level? All the Cj minus Zj values are negative for a maximization problem. And we have found the optimum solution: x1 star equal to 450, x2 star equal to 100, and z star equal to 17,500. Now, before we proceed, we have to see certain other interesting things. that basic variables are x1, x5 and x2. Non-basic variables are x3 and x4. And observe the unity matrix formed with the variables in the basis in the coefficient matrix. Could you find that the table is in canonical form? Yes, the table is in canonical form because the variables in the basis x1, x5 and x2 they form an unity matrix in that order, right? So this is also happens. So what are the shadow prices? There are three original resources x3, x4 and x5. Can you see the shadow prices are 25 by 2, 5 by 2 and 0 respectively. Is it all right? So that is one thing that you observe. And what is the B inverse matrix? The B inverse matrix obviously is this one, minus 1 by 4, 3 by 4 and 0, minus 2, 2 and 1, half, minus half and 0. Is it all right? So we see that the shadow prices are there for x3 and x4. Shadow price is not there for x5. And we also see that the B inverse matrix is formed by the original variables, original slack variables which were in the basis in the first table, and those two things we can compute. So the interpretation of them and further details we shall see in the next class, right? So thank you very much for your patient hearing.